Have you ever wondered what makes the universe tick? Not the big stuff like galaxies, but the very small, the realm of atoms and particles. This is the quantum world, a place stranger than any science fiction. Here, things aren't so clear-cut. Instead of certainty, we have probability. Instead of fixed paths, we have particles taking every path at once. One of the first clues came from physicist Max Planck. He was studying black-body radiation, how objects glow when heated. Classical physics predicted infinite energy at high frequencies, clearly absurd. Planck proposed that energy wasn't continuous but came in tiny discrete packets, quanta. Imagine a glass of water, but you can only have it in specific quantities like spoonfuls. This quantization of energy was a key step towards understanding the quantum world. Planck's discovery opened the floodgates. Einstein used it to explain the photoelectric effect, showing that light itself is made of these energy packets, photons. Let's talk about how things move in the quantum world. In our everyday experience, objects follow a single, predictable path. If you throw a ball, it follows a nice, smooth, anticipated path. But in the quantum world, things are different. According to the path integral formulation, particles don't choose one path. They explore all possible paths simultaneously. Imagine you're at a crossroads, but instead of picking one road, you split yourself in two and travel down both. Then, at the next intersection, you split again, and so on. The path we ultimately observe is just the most probable one, where all these possible paths interfere constructively. This might sound bizarre, but it's been experimentally verified. The double-slit experiment provides compelling evidence for this strange behavior. Let's zoom in even further, to the realm of atoms. In the early 20th century, Niels Bohr proposed a model of the atom that incorporated these newfound quantum ideas. He suggested that electrons occupy specific energy levels, like guests in a hotel with only certain floors available. These levels were quantized, meaning electrons could only exist at those specific energies, and nowhere in between. This model explained why atoms emit light at specific wavelengths, creating unique spectral lines. When an electron drops to a lower level, it emits a photon with a specific energy, corresponding to the difference between those levels. Louis de Broglie proposed that particles like electrons could act like waves too, with a wavelength inversely proportional to its momentum. Electrons, when fired through a crystal, diffract just like waves, creating interference patterns. The wave-particle duality was born. Matter can exhibit both wave-like and particle-like properties. Perhaps the most iconic experiment in quantum mechanics is the double-slit experiment. Imagine shining a beam of light at a barrier with two narrow slits. On a screen behind it, you'd expect to see two bright bands of light where it passed through the slits. But with quantum particles like electrons, something incredible happens. Instead of two bands, you get an interference pattern, as if the electrons are interfering with themselves. Each electron doesn't go through just one slit, it goes through both simultaneously. The electron explores all possible paths, including going through both slits, and these paths interfere with each other, creating the observed pattern. The double-slit experiment highlights the profound difference between the quantum and classical worlds. How do we make sense of all this weirdness? Instead of definite trajectories, we talk about probabilities. The wave associated with a particle tells us the probability of finding it at a particular location. Imagine a cloud. The denser the cloud, the higher the probability of finding a raindrop there. Similarly, the wave function of a particle tells us where it's more likely to be found. This inherent fuzziness is a defining feature of the quantum world. If the universe is so fuzzy at the quantum level, why does the macroscopic world seem so solid and predictable? The answer lies in the sheer number of particles involved. When you have trillions of particles interacting, their individual fuzziness averages out. The probabilities combine in such a way that we observe the consistent, classical behavior we're used to. From the transistors in your smartphone to the fusion reactions in the sun, quantum mechanics is essential to understanding how the universe works at its most fundamental level. As we delve deeper into this strange realm, who knows what other mysteries we'll uncover. The journey is far from over.